Suppose there are two D flip-flops which I have drawn. This is D flip-flop 1, this is D flip-flop 2, and there is some combinational block. Combinational block is nothing but, in our language, in the analogy, the time taken to compute when the input is ready to produce an output, or to make it more simpler for you with an analogy, this is the time taken for the teacher to complete her syllabus. These are the clock periods. So once, say, clock 1 is high, it's a positive edge trigger D flip-flop, right? So first cycle, when clock 1 becomes high, both these flip-flops will become transparent. Transparent means whatever is at the input, they will produce at the output. Q1, it's an open gate, right? So we'll take D1, Q2, still there is no new value given to D2, correct? So it will produce some garbage in the first cycle. In the second cycle, so this is the first cycle, correct? In the second cycle, what's going to happen is, understand, this clock which is making both the gates transparent at the same time is nothing but my college ring or the college bell, which is telling both my D flip-flops to open their gates or to transfer whatever is at its input to its output. When clock goes high again after one more clock cycle, at that point of time, the first flip-flop will take a new input that is nothing but D2, correct? I beg your pardon, Q1 will be equal to D2. Whereas the second flip-flop will take the input Q1, which has passed through this combinational block and has come here. Combinational block is nothing but something like an adder or something like that, which computes, you know, anything, multiplier, anything. So some computation would have come and it will take this as the input. For the timing, let's call this as Q1 computed. So with every clock cycle, my first flip-flop will take a new input. At that same point of time, my second flip-flop will produce the previous output, which has been produced by this combinational block. In order for all this to happen correctly, we have given enough time for this combinational block to compute its computation, and hence I am giving my clock at time equal to 0 to the first one and time equal to t to the second one, or in simple words, I have a clock cycle from time equal to 0 to time equal to t. So this is nothing but my t clock, which is nothing but the time given for my sequential and combinational blocks to compute and get the corrected output. Now, technically, you know that your clock should start here and it should end here. Then it will give your circuit a correct time, or in our language, 1 hour for the teacher to complete its lecture. However, what happens is that this clock is coming from a clock source, which is nothing but PLL, and we expect this PLL to give us the clock at time equal to 0 and time equal to t, which is not practically possible because the clock source, which is a PLL, is made on real chip, correct? And it will have interconnect wires. Interconnects are nothing but wires, and we know that whenever there is a wire is nothing but an RC component, so there will be some delay involved. So PLL are made on real chips and have interconnects. Interconnects are wires, and it also has some inbuilt variations during the manufacturing process. So it cannot produce the clock at exactly time equal to 0 and exactly time equal to t. It might produce the clock to the first flip-flop either before 0, which is this edge 1 which I have shown, or it can also produce after 0. Similarly, it can do the same for flip-flop 2 as well. It can produce before t or it can produce after t. So before 0 I have labeled it as 1, right at 0 is 2, after 0 is 3. This is just the labeling. Similarly for the other flip-flop as well. So what happens is, because of PLL, there are some variations and the clock does not arrive exactly at the time which we want it to arrive. The PLL itself goes through manufacturing variations. It might also have interconnect delays, and this variation will lead to my clock not arriving at the right time to both my flip-flops. And this is nothing but clock jitter. Let's presume that the worst case would be like our analogy, that the clock to the first flip-flop arrives at 3 and clock to the next flip-flop arrives at 4. That means from 3 to 4 is now my clock period, which was initially from 2 to 5. So technically I have lost some time, or my period of the clock has decreased, and this decrease of the clock period, or this variation to be more specific, this temporary variation in the clock jitter, in the clock period is nothing but clock jitter. I repeat, the clock was going to arrive at H2 and H5, but because of some inherent variations in the clock generator circuit like PLL, the clock does not arrive at 2 and 5. It either arrives before 2 or after 2, or before 5 and after 5. The worst case would be that it arrives after 2. That means first flip-flop gets less time. The first teacher arrived late, remember. And the second flip-flop, it arrives at H4. So it arrives early to the second flip-flop. Whereas to the first flip-flop, it arrives late. And now the clock period changes from 0 to 5 to 3 to 4. And this variation, technically in this case it's decrease, but the variation is what we are talking about. This is the worst case. 3 to 4 is the worst case because you reduce your time. So this variation, though it's very minimum in the clock period due to the variation in the clock generator circuit, is nothing but clock jitter.